The title of this clip is Green's theorem, but before we actually even discuss the theorem or the background for the theorem, I want to remind you of something from Calculus 1, which was the fundamental theorem of calculus, or what we called Newton-Leibniz, the Newton-Leibniz formula, which was how we calculated definite integrals. And it said the following. It said that if you have an integral, so now the snake is just good old Calc 1 definite integral from a to b of a function of a single variable. Remember we had things like that? Wasn't life simple back then, huh? So how do we calculate this? We find the antiderivative, right, which we called f, and evaluate it at b and subtract its value at a. Remember this? So this was, sometimes it's called the fundamental theorem, sometimes it's called the Newton-Leibniz formula. In any event, it's a direct consequence of the fundamental theorem, but this is a very important theorem in calculus. It tells you, it relates antiderivatives with definite integrals. It relates the integral part and the differential part of calculus. Okay? Now, let's ignore the details for a minute and look at it, just look at the two sides and try to get a feeling of what the statement is here. The statement is, f is a function, capital F. Little f is the derivative, right? This is true when the derivative of f equals f, right? That's when this theorem holds, right? Otherwise, it's nonsense. So on the right-hand side, you have a function, and you're looking at its values at two endpoints of an interval. On the left-hand side, you have the derivative of the function on the right-hand side, but now you're not just looking at the endpoints, but you're looking at the entire interval from a to b and doing something, and that something is putting the function in a snake. Do you agree? Okay. Green's theorem, as well as two theorems that we're going to see afterwards, which are called Gauss's theorem and Stokes' theorem, are all of this form. On one side, we're going to have some expression involving some function. On the other side, we're going to have some derivative of the function on the right-hand side, but the price from going from right to left is going to be adding the snake. Okay? And moreover, on the right, we're only going to be looking at endpoints or boundary or something like that. And on the left, we're going to be looking at the entire domain. Okay? So this is not something something very precise, what I said now, but I want to write Green's theorem, and then we're going to look at it again and say, hey, it's of the same form. It comes from the same family. Okay? So Green's theorem, so this was the Newton-Leibniz formula. And Green's theorem will be of a similar nature. So I'm not being precise. Let's write what Green's theorem actually says. Okay, so the theorem has quite a bit of setup, and at the end of all the setup, there's going to be the formula which resembles that. So let's start with a setup. I'm going to write everything, and then we're going to go over word by word and explain what they mean. So assume that gamma, I'm going to use capital gamma here. So do you know this letter? This is the uppercase gamma in Greek. Is a planar. Planar means it lives in the plane. Piecewise smooth, simple, closed, positively oriented elephant. No, just kidding. Curve. Told you it was a mouthful. Okay, so we're going to explain all these words. Planar, piecewise smooth, simple, closed, positively oriented. We'll explain all these words in a minute, but to make life simple, just assume gamma is a curve. Okay, gamma is a curve. And let D be the domain enclosed by gamma. So D is the domain such that gamma is precisely the boundary of D. Okay, so we have some domain, and the gamma is the boundary of that domain. Okay, so this was all the geometric underlying details. Now there's going to be a function. So let f, and f is going to be a vector field, a vector valued function, be in C1. C1 means it has continuous partial derivatives, and remember that a field has two components. A field in x and y has two components, which we called p and q. Both are scalar functions of two variables, and saying that it's C1 means that p and q are C1 functions. Okay, remember that? Okay. Then the integral over gamma of the field f dot dr. So this is a line integral of the field f. And the notation we used was f dot dr, and we interpreted this. We said what it means, and I'll remind you of that in a second. Okay? The physical application of this is the work done by f, if f is a force. Okay? Remember this? Equals the double integral over the domain D of the partial derivative of q with respect to x minus the partial derivative of p with respect to y dx dy. Okay, so let's figure out what just happened. What just happened? Oh my God, what just happened? So the first thing I want to add is sometimes you'll see that there's a little circle sitting on the snake. This just is a way of indicating that gamma is a closed curve. Okay? And I'm going to explain what closed is in a minute, but this is just part of the symbol. Okay, so before we figure out all these details, think that gamma is just any curve which is the boundary of some domain D, and tell me if you see that the formula in Green's theorem resembles the Newton-Leibniz formula. Why? On this side, we have a function, in this case, a field. Okay? And we're integrating the field over some curve. Okay? Here, we're doing two things. One, instead of the function, we're taking some derivative of the function. Okay? Remember that f, p, and q are the components of f. Let's add that maybe. Let's add that. Let f of xy equals pi plus qj in C1. Okay, so p and q are the components of f. So what we're doing here is we're replacing f with some form of derivative of f. But the price we're paying is, instead of integrating just over the boundary and ignoring the entire domain, just looking at the boundary, here we're integrating over an entire domain. Or if you want to look at it starting here and moving here, here you're integrating some derivative over a domain. Here you're getting rid of a snake. You're integrating, instead of over a domain, a two-dimensional domain, you're integrating over a one-dimensional thingy, which is just the boundary. But the price is, instead of the derivative, you're taking the antiderivative, some form of the function. Okay? Do you see the resemblance between the two theorems without understanding yet what does this really mean? We'll do examples. Okay? Even before questions, let me write all the details and do a couple of examples, and then I'll answer questions. Okay? So do you see the resemblance? Okay? And we'll see later, if, for example, in Gauss's theorem, there's going to be a triple integral here over a volume, and here there's going to be a double integral over the boundary of the solid. Okay? Same idea. Okay, let's figure out all these words. And I don't want to write all the formal definitions. I just want you to understand the idea. So gamma is a curve. And let's figure out all these words. So planar curve means it's a curve in x and y. It lives in the plane as opposing to curves sitting in space. Okay? So its parametrization is going to be x of t, y of t. Clear? Piecewise smooth. So these two words are part of one expression. Piecewise smooth means it's not necessarily a smooth curve. Remember, a smooth curve is a curve without cusps, where the derivative never vanishes, that has a tangent line at any point. And remember, that depends on choosing a parametrization. We had a discussion of that previously. Piecewise smooth means we're allowing it to have finitely many points at which it's not smooth. So if you take, for example, a square is a planar curve, which is not smooth. Obviously, it has these cusps, right? But it's piecewise smooth. It's comprised of 4 smooth curves that were glued together. Clear? So does everybody understand what piecewise smooth means? Okay? But it's important that it's finitely many smooth curves that were glued together and not infinitely many. Okay? Simple means that it doesn't intersect itself. So a planar curve can look like this, for example, right? But then it intersects itself. So this is not a simple curve. A simple curve cannot intersect itself. So that's what simple means. A closed curve is a curve that starts and ends at the same point. Okay? Now there's an obvious contradiction between being simple and closed. Because if it's simple, it cannot intersect itself, and if it's closed, it intersects itself. Right? Do you see that? So these are actually two words that also come together, and simple closed means that it's simple except for being closed. Okay? So a circle is a simple closed curve, as is a square, but this is not, because this intersects itself at an extra point, and that's not allowed. Clear? So is it clear what simple closed means? Okay. Positively oriented, this is the tricky business here. So remember that a curve has orientation. You can either go in this direction, or you can go in the other direction, right? Life would have been very simple if we could just say clockwise or counterclockwise. But the point is that this positively oriented relates between the curve and the domain for which the curve is a boundary. Okay? So if you just think, let's draw some abstract domain. Suppose this is D. And then the curve surrounding it is gamma, right? That's the boundary of D, right? So being positively oriented means that if I walk along gamma, I have to walk in the direction, that's the positive orientation, such that my left hand is above D, is in the direction of the domain. So if I'm walking here along gamma, in order for my left hand to point at the domain, I have to walk in this direction, which would be counterclockwise. Do you agree? Okay. So why don't we just say, instead of positively oriented, and explain it with walking and lifting your hand and whatnot, why don't we just say counterclockwise? The reason is that gamma is allowed to be comprised of a union of several simple closed curves. Okay, we'll remark that in a second. In which case, we can have a picture not like this, but something more complicated, slightly like, let's say, this. So the domain is now this thing. Think of a lake with a couple of islands. So the domain is this thing. That's D. And the boundary of this domain is made up of three separate curves, right? This one and these two inner boundary curves, okay? Now what would be the orientation? On the outer one, in order for my hand to point in the direction, my left hand to point in the direction of the domain, I would have to go in this direction. But on the inner ones, if I want my left hand to point in the direction of the domain, I would have to go in this direction, clockwise. Do you agree? And likewise here. Okay? So clockwise and anti-clockwise do not capture the notion. Okay, so positively oriented means that when you go along the curve, your left hand pointing to the domain, that's positive oriented. Clear?
Does that have to go with simple closed?
What do you mean, does that have to go with simple closed?
Well, if it's not closed, then it won't have an inside and an outside for the D.
No, it is closed,
Yeah.
but I said it could be made up of several disjoint closed curves, like in this example.
What I'm saying is, if you had the figure 8 like you had before,
Mm-hmm.
then if you walked along, it would depend on where you started for which orientation you would have to go, wouldn't it?
If you had the figure 8, and suppose this is your domain, right? So you're saying that when you walk here, this would be positive orientation. But then when you get to this point, well, depending on if you're thinking of the curve going like this or going like this, right? But in any event, in this half, this would be positive oriented. This is not simple. It self-intersects. Okay? So yeah, this would cause a problem, but it's not a problem because we're only looking at simple curves. Okay? Good? Okay. So all this setup just means that somehow all these ingredients are necessary in order to write a very formal proof. But for us, you can just think of a good old curve, okay? Nothing that causes problems, like having too many cusps, and that takes you into the realm of fractals and very weird curves, and nothing self-intersecting, which causes problems with the orientation and so on. And that's as complicated as it can get, okay? Okay. So this is the theorem. Let's write several remarks. Remarks. So the first remark is gamma can be, sometimes it's stated as a generalization of this theorem. I'll just remark it. Gamma can be the union of gamma I. Union over I equals 1 to n. meaning that gamma can be, just like in that drawing that we made, comprised of several simple closed components. Okay, as long as they fit in nicely in this positively oriented business as together forming a boundary of the domain D. Okay, is this remark clear?
Are each individual gamma I not allowed to touch each other?
Right. Simple, closed, and yeah. Okay, if they're touching, then they're like a self-intersection of a bigger curve or something like that. Okay, let's write like in this thing. Okay, that's what I mean by this remark. 2, the theorem is in the spirit of the fundamental theorem of calculus, or the Newton-Leibniz formula. So we discussed this. Okay, that's all I mean by in the spirit of. And I just want you to keep this in mind, because we're going to see this spirit as we move on show up again in several other theorems. And in fact, we're going to mention this later. They're all a particular case of one much more general theorem in differential geometry, but we'll mention that a bit later. 3, let's look again at the theorem for a second. What it tells you, once we're over all the little details, is that some line integral equals some double integral, right? So the theorem will be used in both directions. Often we'll want to calculate a line integral, and using the theorem we'll transform it to a double integral and calculate that. And in other situations, we will want to calculate a double integral, and we'll transform it to a line integral and calculate that. We'll see examples of both. Okay? So the remark is we will see examples. See in examples the use of green in both directions. Both directions, I mean, let's indicate it very informally like this. Sometimes we're going to use a double integral to calculate a line integral, and sometimes we'll use a line integral to calculate a double integral. Is it clear what I want to say? So I don't have to write too many words. Everybody? Okay. And one last remark, I'm not even going to write it down. There are various ways of phrasing the theorem. They're all very different along very delicate lines, and essentially it's always the same theorem. Sometimes it's phrased slightly differently. So if you open a book and see something that doesn't look exactly like that, think about it for a second and you'll see that it is that. Okay. So sometimes, for example, you start with a domain and say assume D is a domain satisfying A, B, C, D, and E, and then let gamma be its boundary. And then all the conditions on gamma follow, or things like that. But it's still the same theorem. Okay. Okay, so I want to end this clip here and then start a new clip and do several examples in that new clip. So let's stop here.